Here's a picture just like we had in electrostatics. You've got a positive charge that's sitting in empty space and has field lines that point radially outward in every direction. What would happen though if we had some way to just take this positive charge and give it a bump? Just give it one quick shake up and down. What would that do to these field lines? And what would it do to things like a magnetic field? Would we suddenly have one of those? As you may have been able to predict, if we give this a shake, those field lines are going to have to adjust as well. The field lines always have to be connected to the charge and to the rest of the field lines. So we have to have this nice continuous line that follows through. And so if we actually give this thing a bump, we see that those field lines travel out with that deviation that looks almost sort of like a wave. And if we were to keep this thing continuously moving up and down, we could have propagation of this wave that travels out to infinity. And because this is just a moving electric charge, we're going to have magnetic fields that are created because moving charges produce magnetic fields. And so in every single direction, except for up and down, the direction that it's traveling, you're going to have a wave that's emitted, a wave that is part moving electric field and part moving magnetic field. But for the college physics group, we haven't talked about waves yet, so we should do that first. This may seem like an odd place to start with our discussion on waves, but trust me. So we've got a couple of springs here. Let's only consider the one on the left. And we remember from our discussion earlier in the year that springs deal with something called Hooke's law. F equals negative kx. And so the force on that spring depends on two things. It depends on k, the spring constant, which is how springy your spring is. And then it also depends on x, the elongation, which is how much the spring is pulled down or pushed up. As you can easily imagine, if I was to take one of these masses and connect it to the spring, we're going to have a situation where the mass has been connected and the spring has not stretched, so it's going to move downwards. And it's going to accelerate downwards. But as this thing falls, it stretches out the spring. It increases that x in Hooke's law. So the spring force is going to get bigger. And it's going to get bigger and bigger and bigger and bigger and bigger until it's greater than that weight. And then it's going to start slowing this thing down until it comes to rest completely. And now that that spring force is much greater than the weight, it's going to pull it back up. And it's going to go up, 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 up. But as it goes up, 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 that spring force gets smaller because the elongation gets smaller. And then it's going to reach some point where the spring force is zero. And then the weight's going to overtake this system and it's going to fall back down again. And so as you can easily imagine, this is just going to bob up and down and up and down. But what if we were to plot those actual y locations versus time? What would that graph look like? I've saved you the boredom of watching me collect all this data, but what I've done is I've tabulated the y positions for different times. And you can see that I did it for one path down and then back up. So we started at 0 and ended at 0. And if I was to take all of this data and just plot it real quick, put these on some kind of scatter plot with a smooth line, we'd find that we get a very familiar shape. This is a piece of a sine wave. We've started at 0, we've gone up and then back down. So the movement of that mass from the top down to the bottom and back up, and if we continued plotting this out, it would go down and up and down and up, that produced a kind of wave. And that is because there was an oscillation of energy. Looking at our springs one more time, we see that maybe we could have plotted something different. We could have plotted the energy changes for this mass over time. And so currently it has gravitational potential energy, but if we were to let go of this thing, it would fall down, and that gravitational potential energy would turn into kinetic, and it would have that until it reaches the bottom and it stops moving, and then it's all spring potential, which pulls it back up, giving it kinetic until it's at the top and stops moving, and then it's all gravitational potential, and it'll keep oscillating between those as well. So we would have had the same shape if we graphed our potential energy for gravity, our potential energy for the spring, or our kinetic energy, and that is because that's the very definition of a wave. A wave is any repeated disturbance that transfers energy. So the movement of this mass on a spring, that creates a wave. If we had a pendulum that started at the top, swung down and back up, and then again and again, that's going from GPE to kinetic to GPE, and so that also would produce a wave if we were to plot its position versus time. If we took care in collecting our data and were able to find the exact locations for that mass at very exact times and fit that to some kind of curve, we'd find that we would get a formula that looks a lot like this one. So you would have x of t, where x is your position. It doesn't have to be in the x direction. It's really just a displacement, and it's a function of time. It depends on your amplitude, or the greatest value you get to, times the cosine of omega t plus phi. And so this omega right here is your frequency, and it's in radians per second. T is, of course, time, and this phi is your phase constant. And this thing right here is what's determining whether you have a sine or a cosine, blah, blah, blah. So all I did was take these made-up times and plug them into this formula right here, and it gave us a picture that looked like this. And so we can see that part of it goes below the x-axis, and we call that a trough, and part of it goes above the x-axis, and we call that a crest, and it seems like it has exactly one trough and one crest. So we would call this one full wave. If you have a full trough and a full crest, we call that a wave. We also see that the wave oscillates between -5 and +5, and so that is our amplitude. Our amplitude is 5, as we would expect from this formula. And we can also see that it covers just a trough or just a crest, half of a full oscillation in 1 second. And that's because our frequency is pi. A full oscillation would be 2 pi, and so it does half of that each second. And then this last thing is our phase constant, which we have as pi over 2. And that's what determines where we actually start. Because it's pi over 2, we're starting at a minimum, but if I was to go in and change this to be, for example, 0 and not shift it at all, this should look like our normal cosine graph that we would expect. So if I can actually click on this, it would look like our normal cosine graph. So let's look at the frequency a little bit more closely. We see in this picture that we have half a crest, a full trough, and the other half of the crest on the other side. So this is one full wave. It's got a full crest and a full trough. It's just the crest is split in two. If we increase the frequency, though, meaning this pattern showed up more frequently, those two peaks would be squished together. The wavelength would go down, and it wouldn't take as long for us to complete one full wave. In fact, if we doubled this frequency and we went from pi to, say, 2 times pi, what we'd find is that our picture now squishes in, and it takes only 1 second to get a full wave. And then by the second, we've got another full wave. And so frequency and the time that it takes for a wave to complete this oscillation are inversely related. As the frequency goes up, the time it takes for one full wave goes down. And we call those two things frequency and period. And there's a formula that says that frequency is equal to 1 over period, and period is equal to 1 over frequency. To wrap things up, we saw that if you put a mass on one of these springs, it will bob up and down and up and down, and that's because the energy is transferring from one form to another and then back. And if we were to plot that position versus time as it bobs up and down, we would get a wave. We would have some pattern that follows that A cosine omega t form. But what actually determines how quickly this thing bobs up or down? Well, if we were to put a large mass over here and a much smaller mass over here and start them at roughly the same position, we would see that even though they have the same spring constant, they don't take the same amount of time to go up and down. In fact, they're very different. And so the mass makes a huge difference. But there are some other properties that matter as well, if I could actually click on this thing. So if we take these masses away and instead use the same mass on either side, but change one of these spring constants to be much bigger, we would see that that would have an effect as well. Now they again don't take the same amount of time to go up or down. And so that time to go up or down, that's what we call our period, and we can make a formula for this, and we would know that the formula should really only depend on two things. It should depend on the mass and on the spring constant. We could do the same thing for the pendulum as well. Give this some thought before I click to the next tab. In the same vein as what we're doing with these springs, what would be two parameters that our period for a pendulum should depend on? What's going to determine how long it takes to go up to one side and then back to the other? So here you go. Hopefully you guessed right. We've got our two formulas for period. We've got the period for a spring, which is at the top, and it depends on m and k. So our formula is 2 pi square root of m over k. That 2 pi comes from the fact that we're using radians in our wave equation from before. For a pendulum, though, we've still got that 2 pi, but now it depends on L and G, essentially the length of your pendulum and what planet you're on. So those are really the only two factors that determine how much time it takes for that pendulum to go all the way out and back, and similarly how much time it takes for the mass in the spring to go down and back up. And all of these patterns, if we were to plot their position versus time, we would have a graph that looks like a sine or cosine, and that's because we're describing these things called transverse waves. A transverse wave is when the matter moves perpendicular to the way that the wave is traveling. But there are other waves that you could create. You could create a wave where the matter moves parallel to the way that the wave is traveling, and that's going to be our discussion tomorrow. Actually, Wednesday.